Ladies and gentlemen, it's indeed a huge pleasure and a real privilege to ask on stage Professor VijayRaghavan, the Principal Scientific Advisor to the Government of India. Professor Raghavan.
Thank you, Ravi. Good afternoon, everybody. It's not always that one is given a choice between coffee and a talk. And the wise would always choose coffee. So I'm not saying that you are not, but thank you very much for being here. So now, what I'll be talking about is data, knowledge, and understanding. And the point I'd like to make is we always think in today's world that the access to data and its use somehow mysteriously gives us great powers which we never had before. And we are running, sometimes in the right direction, sometimes not, but usually in large packs to access data and use it for a variety of things. So if you go to an astronomer and ask them what they want new kinds of data from all sorts of places. If you ask a medical doctor, again, they want profiles of patients at different levels. A transport person will tell you they want all the transport data and so on and so forth. And then the puzzle comes about how exactly are you going to use this data to make decisions, and how are those decisions going to be implemented, and how do you know they're being implemented effectively or not? And the discussion over the last few years, as data has become more and more accessible, has not focused on that. So what I'll try and do today, and I shaped this talk in the context of what I've seen happening over the last day over here, where extraordinary technical expertise, government expertise have been brought together to analyze what to do and how to do it and so on. So I'm not going to get into matters at that level. I'm going to try and anchor from a science and technology perspective how big data has been used, is being used, wrongly being used, and how in today's world it can rightly be used to empower people. So first of all, data is not information. It's important to keep in mind that we often think data is information, but data has to be distilled and processed to be used and information to come. And that is often not done. So people collect raw data and store it as if it's precious, thinking that that will somehow, it's a major treasure. It is not, unless it's actually parsed, analyzed, compartmentalized in the right way. Secondly, even after you do that, and I gave this example here, this example is of a radio telescope in Pune, a giant meter wave radio telescope. It collects data from the universe. Just having this object collecting that data doesn't do anything. This has to be handled by a computer and sorted out, the noise removed, the signal kept, and then analyzed even further. So information itself, even after all of that is done at the first stage, is not knowledge. Knowledge comes from our linking this information with our deep domain understanding, the history of the field, the history of other fields, and so on. And that is something which requires a lot of work, which is not readily done even today with high-speed computers, with large memories. Even today, that's not easily doable in terms of decision-making and understanding even of different fields. So information to knowledge is a big challenge where human intervention comes in a rather substantial way. Data is invaluable, information is invaluable, but knowledge is important. After that, you take that knowledge and you use it to paint a picture. And this is a picture of X-ray signals. And you say, this is what is useful for you now to use in making a decision. You've thrown away a lot of the data, you've thrown away a lot of irrelevant knowledge, and you put this all in a figure which will go in a published paper or in a document or it will come in your discussions. In other words, you've taken a lot of data, a lot of information, a lot of knowledge, and thrown the bulk of it away. And what to throw away is actually very, very important as what to keep. You could be caught by looking at the wrong set of information and understanding. So knowledge by itself is not understanding. You need to have an understanding of what happens. And then with that understanding, you need to actually make a leap, and you need to then say, this is what I think is happening, despite all past evidence suggesting that this may not be something new. And that is where the human element dominates. And this is an example where Jocelyn Bell, shown here when she was a, I think, 27-year-old graduate student, looked at data coming in from a radio telescope and proposed pulsars from neutron stars as existing. And this is the data she has on the right. From that data, one obvious conclusion was that this was noise coming from some human-made object nearby, and its periodicity should be explainable that way, and it should be thrown away. But it takes a lot of understanding, knowledge, as well as the ability to make this leap and courage to actually do this. And that is not easy. Now, from a human perspective, we have done two things. And one is we have bottom up constructed machines, engineered them in a manner where we, through our understanding of physics, chemistry, biology, construct instruments which can get big data. On the left is an instrument in CERN, the European Collaborative Nuclear Enterprise, where the Higgs boson was recently discovered. And these are built not by some random method, but by a conscious effort to build sensors, remove noise, have extremely sensitive electronics to collect more and more data, and to engineer sources to go around at high speed in accelerators where the data is generated. And similarly, on the right is an example of how that data is looked at in real time at CERN. So bottom-up understanding of the sciences is critical for you to design data collecting instruments. They don't magically come in. They don't commercially happen because these are available. You don't just get cameras shooting things at anything, but you have to decide what you have to look at. Big data, if you ask most of us in India, in the West today, they will think it's a recent phenomena, our ability to get quality information from big data. But that ability is more than 100 years old, maybe even older, few hundred years old, to actually get generalizations from big data. Astronomers did that. Isaac Newton did that. His equations of motion. Kepler did that. His analysis of the planet allowed it to be generalizable. And therefore, one can generalize bottom up to see the way the universe functions. But that, you would argue, is taking the fundamentals of physics, which are generalizable, and applying them to the universe. But many other aspects of our lives, our society, biology, for example, are not governed by these rules fundamentally at a day-to-day level, and therefore other possible rules apply, and therefore data in itself could be of value without any hypotheses coming in to interfere with it. An example which contradicts this and the use of big data in an extraordinary way, which has transformed our lives, is from a trip on a boat in 1835. Charles Darwin here, and Wallace, who at about the same time was in Malaysia, what was then Malaya. These two people looked at what was around them all over the world. Darwin at life in particular, but his other geologist friends looked at the Earth itself. And they made inferences from this analysis of big data, samples from all over the world about how life came about to be. And the theory of evolution by natural selection is an example of the extraordinary analysis of big data, essentially by two people. And that data has changed the entire world forever after that. That information. Darwin's book, The Origin of Species, is one of the few examples in scientific literature whose popular form and whose scientific form are absolutely identical. So he wrote about his big data collection in a manner which everyone could understand. And that's, again, something very important in today's world about data and empowerment, which I'll probably come to. Now, why is it that Darwin's views on data could be generalizable? His point was that all life on Earth has a common origin, and by changes, which he didn't understand how those changes took place, different forms, most beautiful and wondrous, came about on this canvas, and those forms have occupied Earth forever, changing, sometimes disappearing, sometimes coming. How did that happen? How could this connection of how all life and diversity came about be implemented? That required not data at that time, but a deep understanding of biology and how that shared chemistry came about. And that came from the study of genetics. And that's by people such as Thomas Hunt Morgan and others, who found the rules which Mendel had formulated to be applicable to all organisms. So in other words, the generation of big data, the diversity of life on this planet, and the generation of that big data was understandable by looking at the fundamental rules of how diversity came by. But both Darwin and Mendel had no access to the insides of the organism and how this happened. That came about much later by a variety of studies and understanding that the shared chemistry behind all these life forms and all this variation in big data was underpinned by a molecule, DNA, and that DNA structure told us how variation could come about. Now, to summarize then, by just looking at the data around us, by looking at how it changes, by inferring what happens from that, it is not enough. You can come to exactly the wrong conclusions if you just stop there. But by constantly understanding what the sources of variation in the data are, how it happens, and what are the rules which allow certain kinds of variation and not other kinds of variation, allows you to have a deeper understanding and therefore a deeper use later on. If you don't go deep or you disown the deeper understanding, then you end up in trouble. You see all sorts of variations, all sorts of correlations, and then you make causal relationships where none exist. And when data is wrongly distilled, you're in deep trouble, as was the Soviet Union, where their agriculture minister decided that you could convert one species of plant to another by changing the climate or the crop conditions, or that Mendel's laws and genetics were just bunkum, and you could have a different way of increasing productivity in the Soviet Union. That not only caused an agricultural disaster, but it also led to a scientific disaster and the disowning of modern biology for many, many years in the Soviet Union. So the analysis of data is critical, and it cannot be removed from thoughtful human intervention. Another example of this is in the Second World War, where breaking the Nazi code was a critical endeavor, but it wasn't just capturing a few machines and figuring out what the code was and then breaking them. It was not just spies and hard work by some people. It was, again, a deep understanding of the mathematics of data analysis, statistics, which allowed people to break this code. And at the heart of that enterprise was Alan Turing. Alan Turing is also the father of computer science, and he and his descendants, people also contemporaries later on, like von Neumann and others, are examples of how extraordinarily carefully constructed algorithms and mathematics emanating from a deep understanding of those principles, when applied to big data, can be of value. So again, using the tools of big data in a manner where you don't understand their applicability can have disastrous consequences, but using them wisely can be extraordinarily valuable. So what are the questions we ask of big data today? What we ask are, what is its provenance? Is it reliable? Is it good? Is it coming from the right kinds of sources? We want to know where it's coming from. What are correlations and what are causal? That's always something we ask. And how does it help us understand and act? All too often in our endeavors, in our haste to collect data, we collect data whose provenance we are not sure of. We conflate correlations with causality because some of those correlations are very, very strong. People in South India eat a lot of rice, and it can be correlated with everything that they do or what happens to them. But there's a causal relationship which has to be established between the two. How does a proposed causal relationship allow us to act on that data? And that, again, is a big challenge because to establish that causal relationship deduced from big data, one needs to have test beds, test sites, laboratory interventions, large-scale interventions to actually see whether this is meaningful or not. So data and its analysis and use, however high quality it is, divorced from experimental test beds, both natural and constructed, are meaningless. So you have to have these test beds. And investments, therefore, in the fundamentals is very important. Now, over the last several decades, technology has dramatically changed our access to data. Both what we design and collect, like you can see at this room where Chandrayaan is being looked at, its trajectory is being looked at, but also top-down in terms of what we collect in transport, agriculture, weather, climate, and so on and so forth. So how can this collection of data, this huge deluge of data, help us understand the universe better and apply our understanding better? Now, to be good at this, to be good at using data well, we need to understand what the promises and perils of data are. So technology has given us access to data across enormous scales, whether you're an atomic nuclear physicist or an astronomer and everything in between. There's a deluge of data coming in on the large scale. There have been extraordinary examples of success of handling data. Is it that the low-hanging fruit have already been picked and we are sort of worshipping the availability of data disproportionate to what it can yield from now on? An example is, again, the big science experiments which go on. CERN is a tremendous example. For the next set of experiments to be done successfully in CERN will require several-fold more energy requirements, which are several-fold more expensive to test new kinds of hypotheses. And it's not clear whether those hypotheses are worth the amount of effort needed to generate that data. So this is a bottom-up case where one has to examine whether the investments in generating data provide the promised value of discoveries and knowledge. Conversely, the access and analysis of all sorts of data in huge levels, straining the energy requirements of our computational machines, is that wisely done, or can one, by using a combination of data and specific principles, be more efficient? So that's a question about the low-hanging fruit which we need to look at, and we need to ask how we can handle data. I'm not, by the way, saying that big data is not useful. Big data can be extraordinarily valuable, and those who mourn its coming are just absolutely wrong. It's an extraordinary opportunity for new hypotheses, new ideas in sociology, economics, finance, and everywhere to be tested. But it's also a situation where if we don't generate these hypotheses, we're going to be in trouble. Now, I'll go back a little bit to biology, but not because I'm coming from there, but some of the best thoughts about the handling of big data historically have come from astronomy and biology. And in biology, we saw Mendel and Darwin, for example. Now, there's a famous biologist, Sidney Brenner, who died last year. And he has the ability to look at data in the life sciences across different decades, different kinds of approaches, and he comes across with very strong views on data. He has the ability to insist that his opinions might change, but the fact that he's right never does. So Brenner has strong views. So Brenner says that we are thirsting, in biology at least, for a theoretical framework with which to understand big data. And I'll come to an example of why this is true and why this is a problem. We tend to collect data disproportionately in biology and invest disproportionately less in trying to understand the basic principles underlying that. For example, you go to a diabetologist, they will say they want to collect data from all diabetes patients all over the country, and also, control groups and so on. How they want to analyze that, what they want to do, is not usually stated by that same group. So many people believe that more data is better, but history tells us sometimes that least is best. And just as Darwin was an example of looking at more and saying more is better, Mendel and his fundamental principles of biology come from looking at less, looking at a specific plant in his garden and how variation came about from generation to generation. And that was fundamentally of great value. And there are many examples in physics and finance and so on that. So we need both theory and a firm grasp on the nature of the objects we study. So data alone is not enough. An example of how long it takes to build a relationship between theory and data is this one, the Laser Interferometric Gravitational Observatory. The theory that there's a space-time curvature came about from Einstein's theory of relativity more than 100 years ago. That gravity could have a waveform came about as a consequence later on. The ways to test that were proposed many decades ago. The technology to do that wasn't available. And then it took decades to actually build the right kind of technology and collect the huge volumes of data. When that data was collected, sifting signal from noise was incredibly difficult. But once that was done properly, that effort, and there'll be a new LIGO observatory in India, in Maharashtra soon coming up, has resulted in extraordinarily new discoveries on black holes and gravitational waves, which are path-breaking and which were not thought to be a result coming from the LIGO telescopes. In other words, a bottom-up design collection of big data proved a hypothesis. It was very tempting to stop there, but just as with Jocelyn Bell and pulsars, by looking at that data again and again in a way which interrogates it as opposed to just accepting it, has resulted in extraordinary discoveries in a short time after a long time which it took for construction. So I'd like to end soon by saying that, data is important, its analysis is important, but there's a fundamental theoretical flaw in looking only at data and not at the underpinnings of understanding of different disciplines and what their core levels of abstractions are. So, for example, the conversion of data into knowledge is a big challenge. Overall systems approaches, people like the word systems approach and holistic approaches, they claim to solve the problem, but deducing the function of a complex system is an inverse problem which is impossible to solve theoretically. The square root of 4 is 2. It is also minus 2. And when you go to more and more complex systems, you get multiple solutions which satisfy your problem. Which one of them or which few of them are right requires a deep understanding of an area. And this is often missed in our understanding. So in biology, and this is true of sociology, of economics, of finance, you can't escape into holistic approaches and say that, the fundamentals don't matter. In biology, the fundamentals are anchored on genes, But just looking at genes and their expression is not enough. You need to know what the right level of abstraction for your understanding is, and that's the cell in biology. In other systems, it's something else. So what that is and what we train people in these systems are what is important. If, for example, you had taken a neuron and looked at all the genes expressed there, you would not have found out how a neuron works. Electrophysiologists, Hodgkin and Huxley, did that by sticking needles into neurons and solving that problem. So the correct level of abstraction to understand complexity is the discipline, and in biology, that's a cell. Just by looking at all, taking the gene expression pattern of everyone here, or looking at the chair by an electron microscope tells you nothing. You have to understand deeper what's happening. I'd like to end, this is my last slide, on data and empowerment. The result of this handling of data commercially is that those who have distilled the data to information and got knowledge have power. Knowledge and power have gone together in human civilization forever. Those who have knowledge have power. Those who don't have knowledge don't have power. If you can break the Nazi code, you know where the ships are going. If you don't know, with an inferior armed force, you're in deep trouble. So knowledge is important. But knowledge has always been not available to people at large for a variety of reasons, because the training required to get that knowledge has been enormously difficult and requires infrastructure of various kinds. Data and its availability is in some sense a liberating force, a revolutionary force, which can overturn this possession of knowledge only by those who are powerful. The democratization of access to data, the democratization of learning, which allows people to analyze data, and their use of this learning to make their decisions and not be fed decisions, is something which is much more easily possible today by the very tools which analyze data, can also disseminate it and make it access to people irrespective of their economic stature. And therefore, training at the school level, because that's where brilliant young minds are, both in core disciplines where people are interested, and in their ability to handle data and analyze it and distill it and use it, is absolutely critical. India, with its large demography, can do this and have an impact in a few years. Thank you very much. Large young demography. I'd to take questions if you have time. Yeah, sure.
Thank you for a very interesting talk, Suneet Tyagi. I had a question or a comment about, you said, with lots of data, some hypothesis can be proved, but with Popper and the falsification principle on how to discern good knowledge from just pure this thing. Could you comment on that as to how do you see big data, the commencement of AI, where confirmation bias is actually prevalent and will continue to do unless this principle of falsification is put into principle here?
Well, what has happened in astronomy, for example, where it's not easy for you to test out your experiments, and at the other end in physics, where it is possible, in biology, where it's possible, is that when you look at potential causal relationships, you can look at multiple other contexts, and there are mathematical tools which can distinguish between causal relationships and correlation. But that said, I know of no example where extremely interesting things have happened without people being involved, without them having a deep domain understanding. These can be teams of people or small groups of individuals, but that's absolutely necessary. And this is, I think, true. I'm not sure, I don't have an understanding of finance and economics to say whether that's true there also, but certainly it's true of science and technology.
Or can I ask her directly?
Yeah.
Yeah. Anyway, it's working. This is Venkat from Startup Sanatana. I'm just curious to know, like, what's your view on our Gotra system, whatever rishis have done, in the view of big data and other things.
I have a poor understanding of both areas. So you should ask a Gotra expert who knows big data. Yep, okay. Thank you very much. Oh, Harsh has a question here.
Sir, we are addressing technology for business, commerce, and military and social cause. We are not addressing for government and governance, especially for e-governance in election. The democratic process, VVPAT also came, beep sound only giving us a vote. Now I want the technology can give voter verified, paper edited.
Sir, sorry, could I just ask you to just come to the question? Sorry, you've got a few more.
Such a ballot and voting system can be introduced. For that, Aadhaar is the base of data, or socio-economic caste census is the data to use for that. Only I want to know.
Thank you. That's an interesting thought, but I mean, I don't have any comment on how that can be used. There's a census coming up in 2021, I think, a large census, and it's a great opportunity for us as data scientists to analyze previous census results and see how a new one can be conducted and the data analyzed. And that will be a very useful example of putting data science into these kinds of areas. Specifically about elections, I really don't know the details.
Harsh Manglik. Dr. VijayRaghavan, in your presentation, you had a very provocative, intriguing statement which resonated. It was the whole idea of causality versus a straight correlation. And then later down, you also had something, I don't recall the exact words, about is there a theory that ties together big data? So your thoughts on that, do you see such a theory emerging?
You know, this is an enormous challenge. The theoretical foundations in some areas are very strong, and they have typically been bottom-up constructs. And you can construct with those strong theoretical foundations extraordinary complexity. So you can make a supercomputer based on certain fundamental engineering principles and physics principles. The converse problem is a challenge, but is tractable. Look at climate change. By looking at data over several decades, comparing it with historical data, you can make conclusions about what is actually happening. So that's very impressive. You can also, by sending the British Antarctic Survey to point a spectrometer at the skies near the South Pole, detect ozone layer holes, and have policy decisions which fix them. So you can fix big data problems by a bottom-up understanding. So that's terrific. But whether the bulk of what we see in climate change and global warming is fixable in that manner, by fixing each component, does it go back in that manner? We don't have the theoretical underpinnings of that. We went from here to there with a certain route. But coming from there to somewhere sensible may not mean the same things happening. What is that? We are groping in the dark. We are each proposing solutions. So weather and climate analysis requires extraordinary theoretical underpinnings, which are inherently complex. They require looking at flows of complex systems over time and impact of complex systems over time for other reasons. And that's crying for a theoretical understanding. Much of biology, similarly, is crying for a theoretical understanding. The effects of ocean currents on climate is crying for a theoretical understanding. We know very little.
Ladies and gentlemen, please join me in thanking Professor VijayRaghavan.